All right, so this is a walkthrough for the Let's Game Boy challenge in the DoD Cyber Sentinel CTF for 2024. And this is a definitely an interesting one that people will most likely really struggle with because it is such an obscure kind of type of reverse engineering and debugging. So first, I'll go ahead and open up the actual game so we can see what this looks like. I'm using the Same Boy emulator to do this, and I can go ahead and just drag and drop my game on it. I am kind of overlaying this with Windows because this is not available for Unix. But we can see that we awake in the ancient land of Kryptonia. And the first thing you do is you come and check out this little book here. We can see there's a little flag icon. And everything looks all randomized, like you're some kind of Pokemon missing number or something. But there's definitely something there that has been encrypted. So I will go ahead and back out of that and go and explore a little bit. And we can see that there's this wizard fella here who has some wisdom for us. And apparently he's been trying to decipher the book and can't seem to do it. But he has a word. And so this particular challenge has two different ways you can go about it, and the actual word here is going to be used in some way as part of that. But you can either do it statically or dynamically, and definitely just kind of whatever people's strengths are and how they approach it is going to work best. But he says got a word, and you must use a hex, whatever that means. And then he asks you for an answer here, which it accepts hex characters. So we have no idea what this is for. We press enter. It says, nothing happened. So there's our game. And so now we actually need to figure out what's going on here under the hood. And the way that we can do that is by opening this up in Ghidra. This will not work right out of the box because Ghidra does not accept Game Boy games right out of the box. But you can install the Ghidra Boy plugin, or I think there's a couple other options that will actually allow it to parse Game Boy games. So I'll go ahead and open this now. Hit Analyze. And you can see it just drops you into an entry point here with a bunch of crazy registers and things that make zero sense if you're used to dealing with just normal like PC executables, because there's very hardware specific things and functions. But basically what's happening here is this is kind of like a post test, and then it's going to jump into the actual execution of the game itself. So there's a lot of different functions here, and it may be kind of difficult to figure out where we need to focus our efforts to look at. So we can do kind of a combination of static and dynamic debugging of this. And so I'm actually going to close out of this, and instead I'm going to open, packaged with Same Boy, there is also a version that is the Same Boy Debugger. And that actually gives you this handy dandy debugger window that has a lot of commands that you would think similar to other common debuggers. But this will allow us to control the execution and actually debug it while we are looking through the game here. So what we want to do is we want to be able to identify where, if we're going to do this dynamically, we want to figure out where we need to look in order to find the answers that he's looking for. So if we go talk to the wizard here, if you're unfamiliar with, just kind of game dev in general, every time that we are seeing one of these dialogues or this entry form or anything like that, we're in a loop. It's constantly waiting for input from the user, drawing the current state of the screen, and just looping eternally until something happens. In this case, the breakpoint would be that we, happen to be pressing A while we have the cursor in the position to close out this window. So we're going to want to figure out, where in the execution are we exactly? Where in the ROM are we? So we can just go ahead and press I for interrupt, and we can see that it gives us this breakpoint here. And because we're looping, it could drop us anywhere. There could be multiple subroutines and things. But right now we know that somewhere within that loop of looking at the actual input dialog, it dropped us in this one AAA. So I'm going to go back to Ghidra here and press G for go, and we use a file offset of 1 AAA. So we can see that it dropped us into another like do while function. There doesn't seem to be a lot going on here, so we don't really know what any of this is. But again, this is also one of those kind of things where there's like subroutines. So we can go and see what called this function and kind of go up through that stack trace. And there's also a like a backtrace function within the emulator. So if you're wondering kind of like where you are, you can say BA for backtrace, and we can see the call stack here. So this was called, this one AAA, this was called in at 1790. And so we can see that, somewhere up the line, that was called. And so there's a 1 AAA, and that was, referenced somewhere else. But anyway, so we're going to go back to this, this callee here, and we can see that there is our loop, which, doing some kind of dynamic analysis, we could figure out that this is the loop that's actually the dialogue loop. And so, my approach to this would be to kind of click through some of these functions and see, if there's anything that stands out to me is like, what in the world are we looking at? So, so clicking through this, we might see that there is this, this actual dialogue or this dialogue going on here. And there are several different dialogues. These are actually the different dialogues for the wizard. So we'll go ahead and rename this function and call it print dialogue. And you might figure that these are the actual links that it's going to print, of the strings that's going to print. And then we can have a thing here where it's doing some if-else to decide which dialogue to print. So we can call this something like dialogue state. And so this is going to be really important because obviously we want, we can see if dialogue state equals 0, it's going to give us our initial discussion. Otherwise, if dialogue state is not equal 1, then it'll print this, which is like asking, hey, did you ever figure it out? If it's not equal 2, it'll print, nothing happened. So that leaves us with some other dialogue state. We'll just assume dialogue state 3. So it's not 0, it's not 1, it's not 2. Dialogue state 3 is going to actually let us know that we got the correct answer. So that's going to be kind of a key to figuring this out. So let's go ahead and click on this and see where this is referenced. And the only things we really care about are instances where we're writing to that. Like where is that dialogue state being set? And boom, right off the bat, we see dialogue state equals 3 if the cvar1 equals 1. So that means that the answer we gave was correct. So we'll call this answer correct. So if answer correct is being set here, then this function must be check answer, because obviously it's going to look and see if our answer is correct, and if it was, it'll set that to dialogue state 3 and then kick off that dialogue. So this is our check answer function. And so it would probably take a long time to actually fully understand what's going on here. But but we can see that there are a couple of different functions that are being called here, are really just two function calls that are here. So we have a array of 4 bytes, which is coincidentally the size of the input that we are having, and then we have an array of 256 bytes, and then our 2 function calls both call this function function at 0c24. And we click on that, and we see that there are, just a bunch of different loops and things. And this is actually for like just a developer kind of spoiler. This is actually where it is doing the actual RC4 algorithm. But it can be very difficult to actually tell that because there's so much going on there. And it just doesn't really decompile very cleanly. But we can see that our 4 bytes here are kind of like what really matters, and so it's getting the those 4 bytes, and then assigning them to this value local 4. So we'll just call this something like check value, and so it's going to be looking at this check value to determine if the answer was correct. So we can see there's this check value, if check value equals this, and local 3 is going to be, I believe, something else. I think the maybe the length of it. But we can see if check value equals something, which is going to be local 8, we can rename this. We can assume that this is going to be our input. So we'll say if the input value equals the check value, then it's going to call that same function again, except instead of getting 4 bytes, it's going to get 256 bytes. And then it's going to go through and XOR that with something. So we can see that it's going to load that into local 108. We'll just rename this key stream. We'll rename this ivar5. We'll name it I. And then there's this dat 02C8. So we click on that. We can see that this is, some kind of binary data here that's being referenced there. And so that's going to be our encrypted flag. So then it's going to actually save that value somewhere. It has a pointer that's stored at this D000, and then it's going to actually store that in there. So basically what matters is we need to find what this check value actually is. So the way that we can do that, again, now that we've identified kind of where we're looking at, then we can actually see that we're assigning this value here. So we're retrieving that check value using this function 0c24, and then we're doing something with it. So we're going to actually see that that'll be returned from that function, so into a register. So we want to actually figure out how we can retrieve that value. So we'll go ahead in our debugger here, and we can actually go and add a breakpoint there. So we're going to say B for breakpoint. It uses this $ notation you may have noticed. So we're going to put it at 13B5. And then hit continue. And so now in our actual emulator, we can go ahead and submit this. And now we hit that breakpoint. So this is a breakpoint right after the actual execution of that function where it was retrieving that value. So we know that it's going to be in that register somewhere. So it's actually looking at loading the value of the stack pointer, which we type R, we can see registers. The stack pointer points to DEEA. So that's going to be where it's going to be actually loading the answer from, because that was going to be it's going to be popping it off the stack into that HL register, and that's going to give us the actual return value from that function. So if we use ex for examine, and I think we might just be able to do sp like this. Yeah, well, we can actually put in the sp value, which is DEEA. And so if we were calling a function to get 4 bytes and it returned into the top of the stack here, then these 4 bytes at DEEA are going to be popped off the top of the stack into that register, which is our return value from that function. So what that tells us is that this is actually going to be the answer that he's looking for, which we've been able to figure out dynamically now. So we'll go ahead and hit C for continue. He said, oh, you've got an incorrect answer. And so let's try this again now, and we can go to our little dialogue. And so now we can go ahead and hit submit again on this, putting in the answers that we retrieved from that dynamic analysis. We hit a breakpoint again, so we'll go ahead and hit C. And so now we got to that dialogue that says that we got the correct answer. So what's happened is he's checked the answer is correct, and then it calls the function to retrieve the rest of the key stream and decrypt the flag tiles. So we go ahead and look at this, and boom, we have the flag C1 or C4 is magic. Now again, it could be solved dynamically or statically. If people go far enough in the static analysis, if they're not able to figure out the dynamic debugging part, then they may figure out that the actual algorithm that's being used to generate that 4 bytes is the RC4 algorithm, and it does kind of like a shuffling to generate that key stream using the password, which is what the jumble of characters was that the wizard had. So some people may be able to figure out that way, but as you can see, the dynamic method is pretty effective if you know what you're doing and where to look. So I have a little bit of an advantage being able to understand what it is I'm looking at through here. But we'll see how people do in the actual event whenever it comes up. But that is the method for solving this challenge.